tables to, or whatever. Someone's got a tables 2 or 5. Someone 2 or 5 want to say why they think that this is false, and everybody else says they think it's true. Yeah. You cannot mathematically divide something by 0. How do you check a division problem? It's inverse operation. You take your answer, which is here, you multiply it by your divisor, which is there, and you should come back to what you started out with. Is 0 times 0, 6? No. So there is no number that exists that we know of that can define that division problem. This is undefined. So this is false. So tables 2 and 5 were correct. Everybody else should change to false. Okay? So the thing that you have to keep in mind, and this is going to be used over and over throughout today, is you can never divide by 0. Is it okay to, would it be okay to have this? Yeah, that's 0, because 0 times 6 equals 0. That's okay. You just cannot have 0 in the denominator. All right, let's take a look at some of the questions. Is homework graded on completion or accuracy? It's graded on however many you get correct out of however many is assigned. Do you have unlimited attempts on the? Yes, you have 3 attempts, and then I was just told you have 3 attempts, and then you have to do a similar exercise, right? Yep, okay. Is our homework grade affected by wrong answers? Yeah, if you get the wrong answer, you don't get credit for it. Do we need to print out the homework on my math lab? That's up to you. It depends on how you study. If you want to use your homework to study from, which is a great idea, I'd print out your homework and have a separate homework folder so you can go back and review your homework. I take the grades that come right in through the system. Unless you have a real big problem with something and you think you're right and they're wrong, you can show me, as I mentioned in the syllabus, if you read your syllabus. Other projects and groups are done individually. I think, is the last one done? They all can be done individually. How does one deal with the exponent line? Exponent what? Exponent what? 2.3 or 2.5? What do you mean? How do you deal with it? It's totally valid. You can have any number there. X squared to the 1/2. What kind of multiplication problem would I have done to get 2.5? Shane? Yeah, so that's x squared times the square root of x. That's perfectly legitimate. Okay, why does my math lab always sometimes want absolute value? It wants absolute value anytime it asks you to evaluate the even root of an expression. So 4th root of x, square root of x, 6th root of x, any even root, they expect absolute value. Why is any variable to the 0 degree 1, Adam? That has to do with keeping all of the mathematics rules that were created prior to exponent notation consistent, so that if you have something like 2 to the 3rd divided by 2 to the 3rd, if we write that out the long way, we know that that answer must be 1. And if we use the rule of exponents, that's 2 to the 0, because 3 take away 3 is 0. So this is a definition. It's not anything you'll feel in your soul as intuitive. It's a definition, just like we define what the word idiosyncrasy is, okay? Anything to the 0 power except 0 is defined to be 1. Yep.
I was trying to do the homework.
Can we deal with homework questions right after class? That's an individual problem. Thank you. Any other questions? Try yours if you want. What do you mean try it? You have a mental block, okay. 2x to the 4th times 8x to the 4th plus 3x. Okay, let's put this on here so that if you happen to watch the YouTube videos, you'll know what we're talking about. So 2x to the 4th times 8x to the 4th plus 3x. First of all, you have to use your distributive property. And then once you use your distributive property, you have to use your exponent properties to simplify. and then we'll see where we go from there. So we have this whole schmoodle thing times that whole schmoodle thing, and that whole schmoodle thing times that whole schmoodle thing. So we have 2x to the fourth times 8x to the fourth plus 2x to the fourth times 3x. And on x is the exponent 1. Sometimes it's helpful to put it in so you don't forget it. So this is just a multiplication problem. The order doesn't matter, so I'm going to put my constants beside each other in my variable expression. So that's 16x to the 8th. And here I have 2 times 3 times x to the 4th times x to the 1st. So that's 6x to the 5th. And that's it. What'd you do, forget the 1?
No, for some reason I didn't put together the 2x4 and the 8x4. I separated the 2 and the 8.
No, it's all multiplication. Okay. All right. And that's all the questions, right, that are up on the boards. Any other questions haunting you? No haunting questions? Okay. So self-review, self-review. P4 and P5 self-review. This is polynomials like what we just did. X plus 3 quantity squared. That's the type of problem from P4. Can you get the door for me, Mary, please? P5 is factoring, which some of you may need a lot more work than others, depending on how long you've had your last math class. If you've recently had Math 106, you should be in pretty good shape. If you haven't factored for a while, you want to pay attention to that, because today's class, today's class is rational expressions, and this is sort of where we left off at the end of Math 106 last semester, with simplifying, adding and subtracting, multiplying and dividing fractions, algebraic fractions. So that tends to be a little tough for people. So I would suggest that you do not leave the homework for P6 to the very last minute. It's going to take a lot of time probably for you to work through it. So divvy that up a little bit over the next week. You have until next Wednesday before that's due, but don't leave it for the last minute. Don't forget, your quiz number 1 is Wednesday. Try to get here on the half hour, which means at 10:30, I can come right in here and give you the quiz if you want to start a little early, if you're one of those people that always needs extra time just because you're whatever. You're thorough, you really think about things 1,000 times. I hope it's pretty straightforward. If you've been doing your homework and been coming to class, you should be fine. You can bring in a little index card like this. They're located on my door, and put notes on it. I don't care one side, two side. It's up to you. I'm not going to check it. Answers to the syllabus questions due today, they should be in the blue folder. And do you think I'm talking fast today? I am, because we got a lot to do. And please bring graphing calculators to class every day from now on. Yeah. Nope, it is not. Do you have your schedule on the back of your syllabus? Everything is on your schedule, folks. Look at your schedule, okay? Because I need you to know where to go to get these answers instead of asking me. I'm happy to tell you, but you really need to know where to find the answers on your own. Is it clearly indicated on your schedule? Okay, so what is the quiz on Wednesday? What materials? Classes 1 and 2. Okay, all right. So no, I would not quiz you on material that I am giving you today. That's not how I operate. Okay. Anything else? Anything else here floating around in the universe of your brain that you need answered? Shane needs something answered about homework, but I'm going to deal with him afterwards. Anything else out there? Anything bothering you? Any questions? I'm sure you'll have some questions after the end of today's class. How's that? Is that good? Like to keep you stimulated? All right, let's go. All right. So, rational expressions and domains, the great topic for today. Some of you may have seen rational expressions, but I bet domain, unless you've had a lot of high school algebra, may be a new expression for you. This is going to be an idea we use quite a bit in the class. Once we start functions, which is going to be in a couple of classes, this term will be coming up over and over and over again. The packets for this week are located up on that desk. If you didn't pick one up on your way in, you better get it now. That's for the entire week. As you know, when you come in, you should always look at the back table for any handouts. Could you do it quickly, please? Thank you. All right, so who's going to start us off? Tara, want to start us off with number 1? Okay, so this expression, why is this called an expression? It's not equal to anything, right? Doesn't have equals another variable or equals a number. So that's an expression. And an expression is just, you know, every time I think about what an expression is, I don't know why. You know how commercials or ads on TV can sort of make an imprint on your brain forever and ever? But when I was a little kid, there used to be this, it probably would be similar to Subway today, I suppose. There was this commercial where this person had this like huge piece of, like of a Subway or a grinder or a hoagie, whatever you call them, submarine sandwich. And they would, it was actually a commercial for some kind of cold cuts. And they would be piling on the cold cuts and piling on vegetables and different things. And how I think of an expression is sort of like that, or a buffet. When you go to a buffet, you kind of have your choice what you pick. An expression's the same way. You can pick any number you want, any variables, any operations, and put them together. So in this particular case, you would pluck out of your buffet tray 250, the constant 250, the constant 100, the variable x, and what operations would you be plucking out? What other operations would you be taking out of the buffet tray to make that expression? Division, anything else? Multiplication right here? And subtraction, right? So that's what I would be pulling out of my buffet. I'd put them together and voila, here's my rational expression. Note, I've underlined the word rational as a little memory thing to try to help you, the word ratio, because this is the ratio of two polynomials, okay? So a rational expression is the ratio of two polynomials. And a polynomial, right here is a polynomial. It's called a monomial because it's only one term. And on the bottom, you have two terms, and that's called a binomial. Okay, so if you're wanting to know what a polynomial is, make sure you read the beginning of section P4. They'll give you a definition. And he does it really nice. He doesn't put it all out in symbols that looks really fancy. He just gives you a really nice verbal explanation. Okay. So in this particular case, we know that that expression represents the same thing as a cost. So you could now turn that expression into this if you wanted, cost in millions. In other words, you could graph that by having X, which is the percent of pollutions along your x-axis, and a cost along here in millions. You'd get a very interesting graph if you looked at that. But that's not what we're doing today. So find the cost in millions to remove 20% of the pollutants. So what does 20% represent in this expression? What does 20% represent? Right, it says up here to remove X percent of the pollutants. So X is the value 20. So if you're trying to find the cost, in order to evaluate this rational expression, you need to have a value for X. That's the only way you can find the value of that expression. So where you see X in this rational expression, you replace it with the number 20. So you go in, and where you see X, you replace it with 20. Everywhere you see an X. And then you simplify. So you get 5,000 on top and you get 80 on bottom. And when you divide those two numbers, you get 62.5. So if I ask you to complete this with a sentence, you would say it costs 62.5 millions of dollars to remove 20% of the pollutants, blah, blah, blah. Okay, you finish the sentence. Does that make sense to people? Now, why didn't I put in like 0.20 for X? Why didn't I put in like a decimal? How did I know just to put in the 20? Because the unit here, X, is percent. Okay, it's already got the percent, just like the answer here, I know the unit is millions of dollars because that's how it's defined. It's X%. So when I read my problem, I say it's 20%. So that's how I know to put 20 in versus 0.2. Okay. So that's what we call evaluating an expression. The next part says what percent of the pollutants can be removed for a cost of 375 million. It's a little different. Now I'm being asked to solve this for X, or to find what this equals, what value of X will give me a cost of 375 million. So since this thing, all this fancy algebra represents exactly cost, it means that I can set 375 million equal to this expression and solve for X. Okay. So I think that this is an area where a lot of students have questions like, how do you solve this equation? How would you approach it? What would you do? What would you do? Yeah? Okay, remind me your name again? Ricky. Okay, so Ricky says he's going to put a 1 under the 375 so it looks like a ratio. Yup. Yeah, you cross multiply. Why can you cross multiply here? What's this called? Do you know? What's it called when you have two equal ratios of fractions? What kind of an equation? It has a very special name for the cross products idea to work. Reciprocal is when you flip a number the other way like this. These are reciprocals. So I'm not reciprocating anything here. Okay, give me a P. Give me an R. Give me an O. What do you got? Give me a P. Give me another O. Proportion, right. A proportion in mathematics is an equation that has two equal ratios of fractions. And to solve a proportion, it has this property. A times D is equal to B times C. So that's one way to do it. As you can see, when you have a denominator 1 here, it's just like multiplying both sides of this by 100 minus x, because that's essentially what you're doing. Another person might say, well, I want to get rid of my denominator here, so I'm going to multiply that side by 100 minus x, and I'm going to multiply this side by 100 minus x. That disappears, and look what you have. You have your cross product. You have 375 times 100 minus x equal 1 times 250x. Regardless of how you would do it, you wind up with exactly the same equation. Okay. So now to solve this equation, you use your distributive property. And you get 37500 minus 375x equals 250x. And there it's just a straight linear equation to solve. 37,500 equals what? 625x. So x equals, what does x equal? 60? Thank you. So if we had $375 million, we could remove 60% of the pollutants. So this is kind of jumping pretty quickly. It was 62.5 million to remove 20%. We've jumped up to 375 million. It's almost 6 times more to go up to 60%. So it's a pretty costly enterprise. All right. Now, one of the nice things about a graphing calculator, if you take out your graphing calculator, and if you don't have a graphing calculator, I have 6 right here that I can loan for today. You have to run up and take one. Put your name on the board, and I will give you a calculator. When you put your name on the board, I will give you a calculator. Okay. Please hurry. There's more than one marker, so the class is not held up. Cornelius, Ian, Shane, you're going to get a calculator, right?
I am.
We have graphing calculators. Yes, I have the forms. Austin. And Buddha, you should be able to get this emulator on your Mac. We could look at that later, but you take this for now. And if you have a laptop that you're used to, a small laptop you're used to bringing to class, you can bring that on Wednesday, because Wednesday we're going to be downloading something called GeoGebra. I'm working with GeoGebra, and I'll bring in Chromebooks. But if you have your own little laptop that you used to, you can just bring that right in and download it, and you'll have it. Okay. So where was I? Oh, okay. So let's take a look at how our graphing calculators can help us with finding values for rational expressions like this. So it has a really nice feature called a table in your calculator, and I think if you're not used to using your calculators, or even if you are, this is a feature that a lot of you forget about. So we have an expression, and we want to try to, let's suppose we had a table like this to fill out. Well, prior to your calculator or graphing calculator, you would plug in 30, get your answer. You'd plug in 50, and you'd do them all individually. Well, your graphing calculator is a huge time saver. All you have to do is put your expression into the y, in any of your y expressions. So over here you see this little y equals button. So first of all, let me turn on my computer, my calculator. I got to quit. Okay, you hit y equals. Now notice you've got a lot of y variables. You can pick any one you want. I'm just going to use y1, y sub 1. That's how we read that, y sub 1. And I want to enter 250x divided by the binomial 100 minus x. So would someone be willing to lead me through how I enter that into my calculator, and I'll follow your words verbatim? I'm just going to be the little robot here and do what you tell me to do. Anybody want to volunteer? 250 variable x divided by, that's the key, folks. So make a little note. If you're dividing by anything that's bigger than one term on the bottom, you've got to use parentheses, or else this would have said 250x divided by 100, and then they would have, divided by 100, and then x would have been subtracted from the whole thing. Okay, so you got to use your parentheses anytime your denominator is bigger than one term, more than one term. Okay, so now you've entered this expression into the calculator, and let's suppose I just had these first 4 values in my table here. Your calculator can give you the values just like that by setting your table. Okay, you can actually set your table and tell it where to start calculating for this expression. And you do that by going to your second button right here, yellow, is going to give you all the commands that are in yellow above every single key. So you hit second, and you notice right above window, you see the word table set. So now it's saying, where do you want to start your table? Where do you want to start calculating your values? Well, our table's asking us to find how much it costs to remove 30% of the pollutant. So I'm going to say 30. And then it increments by 20, and then by 30, and then by 10. So why don't I just do increments of 10? So I'm going to come down here and say, my values are going to change from one to the other, from one value to the x, by 10%. Now this is where this is really your choice. This is called your independent variable. This is what you plug into your expression, and out comes the cost. So the cost depends on what you put in. The cost is dependent variable. And the pollutants, the percentage of pollutants, is the independent. So you could come over here, and you can see with your horizontal cursors, you can toggle between auto and ask. And if you press enter on auto, for example, I just want to show you what will happen. And then you go second in table, which is right above graph. Then what that does, oops, shoot, I didn't hit second. Second table. What that does is it automatically, that's what auto means, it automatically fills in 30, 40, 50, you see they change by 10, and then it automatically gives you the costs. in millions of dollars under y sub 1, because that's what is equal to your costs, okay? Now, you can go ahead now and take those values right off your calculator and put them right in here. 50 is what? 250 million. 80 is, how do I read 80? 1,000 millions, right? What is that equivalent to, 1,000 millions? A billion, right. But this is in asking you to put it in millions, so you're actually going to put 1,000 millions. And then 90% is 2,250 millions. Okay. So that helped me with the first 4 values in my table. But now notice my increments are changing. I'm going by 5, and then by 3, and then by 1, and then 0.1, and then 0.001. 0.01, excuse me. So this is where this other feature of your table really comes in handy. You go back to your table, second table set. You say, okay, I'm going to start at 95 because that's the next one I want to figure out. I don't really care about now trying to define my increment because my increment is changing from one value to the other. So that's where I go down to my independent variable here, and I scoot over to ask, and I hit enter. So now it's going to ask me, what value do you want to plug in for x? And when I plug in that value for x, it's going to automatically give me the value for my cost. So now I go over to second table, and now it's saying, okay, what value do you want to fill in your table? And what's the next value? 95. So let's put in 95, 95, and the minute I hit enter, there comes my value for the expression, my cost. So as you can see, this is a great time saver. So why don't you fill out your table for the next 3 values of x, and then we can take a look at what you got as a group. Okay, so for 98, we've got 12,150 millions. 99% of all the pollutants are gone. 24,750 millions. Boy, this is going to cost the taxpayers quite a bit. 99.9. 249,750, and then 99.99. What does that mean? 2.5 E6. Austin?
2.5
times 10 to the 6. Right, this is how they write scientific notation. So 2.5 times 10 to the 6th. Okay? Huge! Huge. So what happens if I put in 100? Let's see, is that the next question? Okay, the next question is, what happens if I ask the calculator? Let me go to my next, is it down here or on my next page? Here we are. What happens if I enter 100 into my calculator? Error. Does that mean, what does that mean? We can't take out 100% of all pollutants? Does our calculator knows we can't do that? No, our calculator doesn't know that. Doesn't even know the context of the problem, right? Well, what would that tell us about the cost of cleaning up the river's pollutants? It's cost prohibitive, right? It's so huge. If you were looking at this graph, it'd be blowing up to infinity. It would be increasing without bound. But why did we get the error? That's the key. Buddha? Remember what we just said with 6 divided by 0? We couldn't do that? Well, look at our expression if we try to put 100 into our expression. We get 25000 over 0. No can do, right? We can't do this. It's undefined. So that's why the calculator gives us an error. But if we were looking at what was happening to our cost, it's just gone out of sight. It would be impossible. Okay. So the value of this rational expression when x equals 0, it doesn't have one. So we say, whenever we see a rational expression that looks anything like this, anything, that this expression is not defined at the value x equals 100. So when we write an expression like this, a rational expression, beside it, and what you'll be doing for homework is it will be asking you for the excluded value or values. That's why I put the S in parentheses. The excluded value from this is that x cannot be 100. Okay. Every other number, now if we take this out of the context that we're in right now, if this is just a mathematical expression and it doesn't have the meaning about pollutants and costs, if I was just looking at that expression, I could put any number in the world in there on the real number line, and it would have a value except for one number, which is called 100. That's the only number that would gunk this little expression up. It would jam it. Doesn't know what to do with it, cannot compute, like those computers, those robots that go crazy. It would start going crazy at 100. Okay? Yeah, Kyle? I said, excuse me, I said outside of the context of the story, just as a mathematical expression. In the context of the story, it's very different. If I asked you in this context of the story, what else wouldn't be allowed in there, Kyle? Yeah, anything below 0, actually, right? You could just not remove 0%, right? So in the context of the story, all of the excluded values would be negative numbers and the number 100. But as a mathematical expression, just pure and simple vanilla expression, everything's allowed except for 100. Okay, so you just got to, in your book, they're going to be probably just giving you a bunch of expressions and saying what can go in here and what can't go in there. And then you might have some stories, and that would be a different answer if they have a story to it. Okay? Okay. All right. Any other questions? All right. So this leads us to a very important idea that we're going to be using over and over again this semester. Underline and in bold is called the idea domain. And this is going to, like I said, when we get to functions, which is going to be real soon, the idea of what is a domain and being able to look at a graph to see what a domain is going to be used over and over. But for right now, with these rational expressions, this is going to be the definition of a domain. Boo, do you want to read that for us? Right, so this is what Kyle was getting at. Okay, Kyle was thinking of the problem we were working on, which had a context or a story to it. And in that story, we couldn't have a negative percentage of pollutants to remove. But the rational expression in and of itself has a set of numbers we can plug in with one exception. So the most critical idea here is that a domain is a set. So when I ask you what the domain of this particular expression is, you represent it this way. You say the domain is a set of all x such that x cannot be 100. Okay? And it's understood that x is a real number if you don't state it. Okay? Yeah. This expression right here. Nope, because this includes all numbers except for 100. So if we were looking at this is not referring to the problem, the application, it's just referring to this expression, okay? So what this says is that if you were on the real number line, you'd be out here at 100, and you'd have an open circle, and every other number to the left of 100 you could put in that expression, and every number to the right of 100 you could put into that expression, and your calculator is going to give you an answer. It's only at 100 that you get the answer error. Okay. Any other questions? Okay. So sometimes it's nice to start off with an application, and then when you try to generalize, it can get a little confusing. But this is just called a rational expression. It has no story to it. All right. So when can a rational expression not be defined or evaluated? When your denominator is 0, right? So that's all you have to hold on to right now. That's the only thing you have to worry about when your denominator is 0. That's the only thing you have to worry about. You don't have to worry about the numerator. You don't have to worry about anything else. So at your seats, I want you to come up with your own rational function. Oops, another typo. I'm so used to saying function. Your own rational expression that has a domain of all real numbers except x cannot be 10. So you make up your own. Okay, so who haven't I heard from today? Someone want to volunteer that I haven't heard from today? Ellie? 22x over 10 minus x. That works. Anything different than that? There's a zillion possible answers, and that's a real number too, zillion. Okay. Anything else? Everybody has 22x over 10 minus x? Oh, so, okay. How about, did anybody have anything other than 10 minus x? What did you have, Buddha? 3 squared or 3x squared? 3 squared minus 1 minus, that's not a rational expression, right? It has to be the ratio. And this thing is defined in the denominator. So that's the same thing as 10 minus x, isn't it? Okay, so, all right. I'm asking for anything different than 10 minus x in the denominator. Anybody? Shane? Same thing. Okay. All right, let's move on. All right. Okay, so sometimes we can get denominators that are a little more complicated than 10 minus x. And we have to do a little more work to try to figure out what's going to make them 0. Okay? So this first denominator here is x squared take away 25. And I'm sure we can look at that and figure out what value of values is excluded, right? What value of values would be excluded here? Oh, someone rescued you. I heard 5 really bold, and then the and negative 5. You know how many times you forget and negative 5? Yeah, because of the absolute, a lot. So let's first put in the answers. The excluded values are +5 and -5. So some of you are working ahead in the lecture notes. So if you forgot the -5, write yourself a really nice little love letter to yourself, okay? Not to forget it. So how would I write the domain? Someone help me write the domain. Actually tell me what I would write. I'm going to be the writer, and you be the person to tell me what to write. How would I write the domain? Lenny, I've heard from you. I'm trying to get other folks. And I've heard from Adam, and I've heard from a lot of people. Sam, how about you? Can you help me with the domain? Yep, the fancy parentheses. Yeah. Yeah. Okay, that's the domain. It's a set, first of all. You see that, those fancy parentheses, the curly braces. So it's all numbers. So if we had this on a number line, we'd have an open circle at -5, an open circle at +5, and we would be including all the zillions of numbers in between, to the right of 5 and to the left of -5. So if we were looking at a graph, there would be something really funny happening around -5. Notice I have a dotted line in a +5. Something really funny happening in there. We'll be looking at the graphs of these types of things later on in the course. Okay. But for now, how about if you couldn't figure out by looking at it, how would you figure out what would make that denominator equal to 0? How would you do it algebraically? What would you do? You could factor it, right? But the question you're asking is, when is x squared minus 25 equal to 0, right? That's the question of the hour, right? When is the denominator equal to 0? So you set your denominator equal to 0. And yeah, if you factor it, I guarantee if you factor the left side, because the left side is an expression, you will never, ever forget both answers, both of those answers. Okay, if you scoot the 25 over there and have x squared equals 25, I know what you're going to do, and I'll show you in a second. But stick to factoring. That's a really nice, easy thing to factor because it's the difference of two perfect squares. So those are the factors that you like because they look identical, x and x, 5 and 5, except for one has an addition sign and one has subtraction. Now to finish that problem, you say, when does x plus 5 equal 0? Well, that's just a linear equation. You can drop the parentheses. It's when x equals negative 5. You subtract 5 from both sides. When does x minus 5 equal 0? When x equals positive 5. So there you can get your answers. You'll always have two answers when you do it that way. But what does a typical student do? And I know none of you are typical because you're all exceptional. I know that. Okay. So this is what a typical student does. They go, okay, x squared equals 25. And then they go, oh yeah, to undo a square, I do its inverse. And they put this symbol in, like this. And they rightly say that the positive square root of 25 is a 5. That is correct. But this is where the error occurs, right there. It's absolute. Remember, we talked about this on Friday. The square root of x squared is defined to be the absolute value of x because we don't know if the thing being squared is positive or negative. So once you do this, then you say, oh, there's two numbers I can put in here for x. X could be a positive 5 because the distance from 0 to positive 5 is 5 units, or x could be negative 5 because the distance from negative 5 to 0 is 5 units. So when you have an absolute value problem like this, you take the stuff inside, which is called x, and you set it equal to positive 5, and you set it equal to negative 5. It has two results. So the key, folks, when you're solving these types of quadratics, this is called a quadratic equation where you have a square on one side and a constant on the other, is that if you use the square root symbol, you've got to remember that what comes just below that is not x, it's the absolute value of x. And then you'll get your two answers. Personally, I'd rather factor it if it's a difference of squares like that. But this is, I remember one year trying to teach us some 096, and I had a heck of a time. But and this problem plagues algebra students forever because you're really never properly taught that the square root of x squared is the absolute value of x. You get out of it, your books get out of it by saying assume x is positive, but we can't assume that anymore. Yep, did you have your hand up? Oh, scratching, okay. All right, so it's up to you what you prefer to do. Some students say, can I just do this? X squared equals 25. Can I go right down here like this, Linda, and do that without showing the work? If you can do it without showing the work and you can remember it, all the power to you. That's great. The key here is that anytime you have a quadratic that looks like this, x squared equals some kind of constant, your answer is always going to be x plus or minus the square root of whatever k is. Okay, so if k is a perfect square, you get a nice rational number, integers like this, 5 and negative 5, rational numbers. If k was the number 7, you'd have plus or minus square root of 7. Okay, so that's the only tricky part of that denominator. Okay, so how about this? Does anybody remember, P5, by the way, is factoring. So if you need some factoring help, P5 will help you out. Does anybody remember how you factor x squared minus 6x minus 16? Because we want to know when that's equal to 0. Now that's a little harder to figure out by trial and error. So anybody remember how to factor that? X squared minus 6x minus 16? Sam? Okay, and what would that be? Negative 8 and positive 2, that gives you your negative 16 when you multiply them, right? And x and x. So now to get our excluded values, we set each of those factors equal to 0 to see what can't be in the domain. 8 would make that 0. The number 8 would make that 0, which therefore would make the denominator 0. And what's going to make the other factor 0? -2. So our excluded values, x cannot be 8, and it cannot be -2. Okay? So our domain for this expression is the set of all x, except such that x is not 8 and x is not a -2. You can use and, you can put a comma, you can do whatever you want. Okay, I'm not that picky. I just want to see both values and the fact that it's a set. All right, you'll have lots of practice. You'll have lots of these for homework to do. Okay, anything else? Any other questions on how to find the domain and the excluded values for a rational expression? Yeah, Mel? You can use whatever you want, yes. I just put a semicolon in there to be, I don't know, weird. I think semicolons are used when you have sort of like two complete sentences that sort of have the same subject, right? Sort of thing. And so here, right. So x not equal to 8 and x not equal to -2 are it's almost, they're definitely connected to this idea of what's excluded. So I feel like it's okay. All right. Not that we're in an English class. Okay. My last class got all bogged down when I reduced this. I don't get what you're doing. Why are you doing that? So let me ask you, we're now looking at simplifying rational expressions, which this is a rational expression. Simple. It's a monomial 12. It's a constant divided by another constant. We call these fractions, and we know how to reduce this. If I ask you to reduce this, I think most of you will tell me it's what? 4/5. So this is how I write it, 4/5. Okay, there's 4/5. Okay, what's this? I understand, right, okay. So 4/5, 4 divided by 5. Ha, 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 ha. Well, what's this? This is easier. Mind over matter, right? Mind over matter. Okay. All right, so most of you do that, and there's no problem. And so I don't know why I created such a stir in my first class. I guess because we were looking at the concept behind it. How did you get that? What were you really doing when you reduce a fraction? This is called reducing a fraction, and a fraction is a rational expression, to lowest. Notice it's a superlative. Here we go back to English, to lowest terms. What did you actually do? Almost. Almost. Divide, remind me, is it Ian? Ian said divide by the, these terms are often confused. Divide by the common multiple of numerator and denominator. Well, multiple of 12 and 15, it takes me a while to get there. I think, what would it be, 60? Is a multiple of 12, and it's a multiple of 15. So it's not the word multiple. Factor, right, it's a common factor. You're finding a factor that's common to the numerator. So you can factor the numerator. We just talked about factoring. And you can factor the denominator into primes. And then you find a factor that's common to both. So it's dividing out. You're literally dividing by the number 1. So you can take 12 and you can represent it as 2 times 2 times 3. And you can take 15 and you can represent it as 5 times 3. And this is where a lot of people are weak, is in their fractions. When you have a multiplication problem, so in other words, when your numerator is all factors and your denominator are all factors, I should have said are, when you have all factors, you can split that up in any way. So in other words, I can rewrite this like this. I don't change it at all. And 3 divided by 3 is a number 1. And we usually do this kind of thing. That's kind of the notation many of you learn somewhere in school. And so what you're left with is 2 times 2, which you write as 4, divided by 5. Okay? So as long as I have multiplication all the way around, I can look for the same thing. But the thing is critical, folks. Notice there's no addition signs or subtraction signs anywhere. You can multiply by 1 without changing anything, and you can divide by 1. That's the key. So we're going to use this idea, and the idea that we're using is that we're dividing the top and bottom by 1. And this guy named Aaron Einstein came up with the term foo-foo, which means fancy form of 1. So he called this a foo-foo. So you find the foo-foos between the numerator and the denominator, and those become your 1s. Okay, so the key here, what did I do? Factored each numerator and denominator into prime factors, divided out by 1. So let's take a look at this first one. First it says identify and exclude values from the domain. So the before, and that says mandatory. So before I even start this, what can the denominator not be? The denominator cannot be 0. So I have to factor that, which looks like this. So my excluded values are a -4 would make that denominator 0 if I put a -4 in there, or if I put in a +2. So those are my excluded values. My second one, my excluded value is simply -4. It's linear, so I only have one value instead of 2. So this is a second degree down here. Often I will have 2 when I have a second degree. And here's a linear because it has an exponent of 1, so I just have 1. So that little exponent sort of gives you a little hint as to how many excluded values you may have, the maximum number. Okay. So how am I going to factor? Now, here's why it's important, folks. Because you see this denominator? This is a single fraction right here. It's a single fraction, one numerator, one denominator. I would have added 2 fractions and subtracted 1 fraction to get that. I would have added 2 fractions. Nothing else to do? Hello. This is President Pura. Say hi, Bob. Hi, Bob. Hey, Bob. Hi. All right. So I use this little gimmick. I call it a gimmick because for some of my students it works. Anytime you have more adding and subtracting, I say, put your arms around it. And what I mean by that is this. Put parentheses around it. And unless the stuff in parentheses in the top is identical to the stuff in parentheses in the bottom, you cannot find a foo-foo. Because the evil temptation when you don't put your arms around it is to start going like this. X squared with x squared, x with x, a 2 in there and a 2 in there. Okay? That x squared plus 2x minus 8 is the denominator for x squared, 3x, and -10. Those would have been the 3 fractions I would have squished together to get that single fraction. So now, after you put your arms around it, you can factor each one and keep some arms going here. So this first one is x plus 5, x minus 2. Again, if I was teaching Math 106, I wouldn't go this fast because we'd be learning how to factor. But again, this is a prerequisite skill, x plus 4, x minus 2. So now my arms are around each individual factor. These are all multiplications. If I wanted to, I could split this up. You don't have to, but you could split it up like this. You don't have to, but you could, because that shows you nice and clearly where your foo-foo is. Here's your foo-foo, your fancy form of 1. Most of us just choose to go like that with the slash. I think it's really critical to remind yourself with a 1 that you're dividing by the number 1, and that's why it's not changing. So your final answer here, and please keep your arms around the x plus 5, and keep your arms around the x plus 4, because if you don't, you then fall back into the temptation of canceling the x's. X plus 5 is very different than x plus 4. They have no factors in common, beside 1. You could put a 1 in front of each of them and it wouldn't change. So in other words, if you put a 3 in for x, this would be 8 over 7. Can't reduce that. If you put a 2 in for x, it would be 7 over 6. You can't reduce that. If you put a 10 in for x, it's 15 over 14. It's already prime. Both factors are prime. Okay? So those are really the key ideas. So what about this one? How do you simplify x plus 8 over x plus 4? Already simplified. So I call that already simplified, silly. See why I don't want to be on YouTube? I get in trouble. Already simplified, silly. All right. It's already simplified. Right. It's already done. Can't. All right. So we can't take a few minutes to write about everything you remember about adding, subtracting, multiplying, and dividing fractions, but we can summarize real quick. What do you have to remember about adding and subtracting fractions? What's the key idea about adding and subtracting anything in mathematics? Regardless of whether it's fractions or radicals or numbers you're lining up, what's the key idea? They have to be the same. We call them like terms when we're doing things like 3x plus 2x. For homework, you had to do like radicals, like 2 square roots of 3 plus 4 square roots of 3, okay? With fractions, they're called like denominators. They've got to be like. Everything when you're adding and subtracting must be like. Multiplying fractions, well, multiplication is the most forgiving. If you have 2 fractions or any 2 numbers, it doesn't matter. You just multiply them straight across as they are. They don't have to have the same denominators. And when you're dividing, division's probably one of the hardest operations to really, not just for fractions, but in general. We change division to multiplication because we like it, but you can't just change a division problem to multiplication without also changing the divisor to its reciprocal. So you multiply by the reciprocal of your divisor. So essentially you have two operations, adding or subtracting. You can change subtraction to addition of the opposite, and any division can be changed to multiplication. So those are really the 2 main operations for fractions. All right, so let's see how we add and subtract these monsters. They look really scary, but they're not. So don't forget to identify the excluded values from the domain. So on that first fraction there, what numbers would I exclude? How many do you think I can get out of that first domain? How many excluded values? Just just this first one right here. This first denominator, I'm sorry, the first, how many you think? 2, right? Because you see that little exponent 2? So that will help to remind you that it's not only 4, but it's -4. So we can't have a 4 there, and we can't have a -4. And lo and behold, the second fraction, -4, also works there. So our domain here would be all numbers except for 4 and -4. Now we're going to actually factor everything. I'm going to factor that first numerator. It's the difference of perfect squares. Those are the ones I like to factor because they're real quick. I take the square root of x squared, x times x, and square root of 25, and I put a plus and minus. And then x plus 4, x minus 4. Okay, and then I change division and multiplication. My denominator becomes my numerator. And now x squared plus 6x plus 5. 5 is prime, so the only factors of 5 are 5 and 1, and those happen to add up to 6, so I'm golden. I got x plus 5, x plus 1. And you can just now join them with one big long fraction bar because everything means multiplication. And now you look for your foo-foos. Any foo-foos, top and bottom. Fancy forms of 1. There's an x plus 4 in the numerator and an x plus 4 in the denominator. There's one big foo-foo. Any others? X plus 5, x plus 5. So That means I have 1 times x minus 5 times 1 on top, which is x minus 5. I keep my arms around it. And on bottom, I have 2 factors, x minus 4 times x plus 1. Okay? And that's how you simplify that division problem. Not simplify it, how you actually perform the division. Okay? So let me give you, and I think we have another one to try, don't we? Now, subtraction is a little different story because we have to make them like. Let me just give you a little like word of advice. P6, the homework for P6 is due when? Next Wednesday, okay? Which is a week and 2 days. It's also probably a very time intensive because these problems can't be done willy-nilly like some of the ones you've been doing. Okay, so make sure you spread out P6. Don't try to do it all at once. Spread it out over the next week and 2 days. Okay. So we need to make these fractions common, but the other thing is I have a subtraction symbol here. These can get you in trouble. So what I would do is I would just change any subtraction problem into adding the opposite. Just like that, I'd put the plus and I put the minus right in front of the 2 so I don't forget to distribute that negative sign. Okay. So the first thing I have to do is I have to factor both denominators. So let's do that. So let's see. Someone want to help me with the first one, if I can factor it? First one. X plus 2, x minus 1. Do I have any agreement on that? Yeah, okay. And now I've changed my subtraction to adding negative 2 in the top. And now someone different. So the first denominators, factor each denominator, okay. And what about the second denominator? Someone different want to help me out with this one or help us out? What did you say? Plus 4 minus 1. Let's try that. Plus 4 and minus 1. Do we have agreement on that? Okay, plus 4 and minus 1, when I multiply them, would give me a negative 4, and I got a plus 4. So I know when I see a plus 4, my signs have to be the same. So someone else suggested minus 4, so let's try that. Does that add up right? Yep, 4x and 1x, negative 4x is negative 5x. Okay. So now we're going back to Ian's word, multiple. We need to find a common multiple. And this is sort of like the reunion idea with the Beatles. If you think of each one of those factors as a different Beatle, who's coming to the reunion? If you look at each of those factors as a different Beatle, who would be coming to the reunion? What would their names be? X minus 1 would be coming. Do I have to put x minus 1 into the reunion twice? No. Who else? X minus 4 and x plus 2. That is your lowest common multiple. There you go. Okay. It's just the union. Okay. So now this is the tricky part. You now have to change each fraction to an equivalent fraction. This is where the time comes in. With this denominator. Okay. So I've got to take my first fraction, which is x over x plus 2, x minus 1, and I need to make an equivalent fraction. This is like going from 4/5 to 12/15. You're raising to higher terms. You want to now make it into a fraction that has x plus 2 in the bottom, x minus 1, and x minus 4, so that you have your common denominator or your common multiple. So what factor does this denominator have that this one doesn't? What's the only factor that it has that the other one doesn't? X minus 4. So you multiply top and bottom of this one by x minus 4. and that's their equivalent fraction. So now I come up here and I say, okay, I'm going to get a little lazy. My first fraction, when I turn it into an equivalent fraction with the common denominator, but now I'm just going to do this, LCD, because my hand's getting really tired and this problem's getting really long, and I'm just going to call it LCD, just for now. And now I want to add it to a new fraction with the same denominator. So let's take a look at the second fraction. Negative 2 over, help me, I've left my visual screen here. What's the denominator for negative 2? X minus 4, x minus 1, okay. And I want to convert it to this. I want to make it into an equivalent fraction that has this in the denominator. Well, it has x minus 4 and it has x minus 1. So the only factor I need to multiply top and bottom by the form of 1, I'm not changing it, I'm multiplying it by a form of 1, is x plus 2 over x plus 2. So that's negative 2 times x plus 2. See why I wanted you to put the negative sign there, so you distribute it through. So I go up here and I write negative 2 times x plus 2 over the LCD. So now I say, okay, I've got the same denominator. I put one big long fraction bar like that. And now I go to town. X squared minus 4x minus 2x minus 4 is x squared minus 6x minus 4 all over my LCD. Now I cannot factor this. That can't be factored. So now I just throw in my LCD in factored form. And that's it. I put a big circle around it. Okay? You don't have to multiply this out. I'm not expecting you to multiply that out. Okay, so don't forget, Wednesday's your quiz. You can bring in index cards. Please bring your graphing calculators, and could I have one at a time get each of these calculators? From Shane and Tashi, Cornelius, you can just erase your name, yep. Buddha, Ian, and Austin. Cornelius, all right. Tashi, Buddha, Ian, and Austin, thank you. Thanks. Okay. I'm in my office. If you need any help or you have any questions on my math lab or anything about Wednesday's quiz, please bring your blue folders up and throw them on the back table as you leave. One person from each table would be great. And don't forget, I have everything on YouTube.